welcome everybody to this electronics unit lecture 1. And we're here at LSU, and my name is Jill Juno, so I'll be providing the majority of the content for the PowerPoint slides, as well as getting some help from my colleague Josh Collins, who will also be jumping in, but he'll also be doing the activity portion of this lecture. And then Dr. Guzik is currently here right now, as well as another student that we have here with us. So we'll be working our way through this. Give me 1 second here to get started. So as you heard, the lecture is being recorded, which I learned from the last meeting that apparently anytime you guys chat, it is also recorded, so just be aware of that. So we'll be doing the Introduction to Electronics section today, and then one with some more details about different electronic components. This is a very basic, high-level introduction to this. Some people may already have a pretty good background in electronics, and that's awesome if you do, and hopefully you can help your teammates out that may not know as much. But for those of you that this is going to be very new to, maybe you've seen some of this in your physics class, that's okay. I know whenever I was an undergraduate, I also did not have any previous experience with electronics or with programming. So certainly this is a great place to get started on it. And electronics is quite an art to learn, as well as what I would call just lifelong learning. I still learn things every day, and every time I'm working with them, I learn something new. So there's going to be some struggles, but hopefully you are able to learn how to work with them, as well as how to read documentation and data sheets with them over time. So you'll get better at it. Just stick with it, and hopefully the most important thing is to be safe with working with these different components. All right, so here we go. We're going to get started. If somebody has a question, Josh is going to be monitoring the chat, so feel free to ask questions there, and then maybe I'll pause a couple section times for people to ask questions. All right, so let's get started. What should you already know? And I see that there's a question mark there, which is important because maybe you don't know all of this, and that's okay if you don't as well. But definitions of electrical quantities. So today we're going to be talking about electric potential, which is measured in volts, millivolts, or microvolts. These are the standard ones that we'll be working with in this course. So just a reminder, millivolts, milli is 10 to the minus 3, and micro is 10 to the minus 6. Electric current, measured in amperes, milliamps, or microamps. Electrical resistance, typically measured in ohms, kiloohms, or mega ohms. And again, kilo is 10 to the 3, mega is 10 to the 6. So you can see that the 10 to the 3 and 10 to the minus 3, those things tend to cancel, as well as the micro and mega. And then electric power in watts, kilowatts, milliwatts, different types that you'll see. And then we'll also be going over Ohm's law, which might be like one of the most important laws of with electrical engineering, as well as power relationships. And we'll be taking a look at DC currents, or DC circuits, which is direct current, which is what we will see for the most part with the balloon in the balloon program when you're working with batteries. But then we'll just briefly be talking about AC, or alternating currents, which is more like what you would find whenever you look at the power coming from a wall socket. So to start off with, electric potential, 1 volt is equal to 1 joule of energy per coulomb of charge. We're not going to get into too many details on that, but just some basic examples. Whenever you look at a flashlight battery, if you were to measure that, it's on the order of 1.5 volts. Again, direct current when we're working with batteries or power supplies. Car battery, 12 volts. Wall socket, again, that's where we get into alternating current, 120 volts. And then if you were to look at the overhead power lines, it's really 6,000 to 250,000 volts AC. So quite a bit difference. That's why they tell you to stay away from power lines, obviously. But same thing with wall sockets as well. So for current, we always refer to this in amps. or ampere, and it equals 1 ampere is equal to the movement of 1 coulomb of charge per time interval of 1 second. Again, when we look at those same kind of things, you know, flashlight, we're looking at 300 milliamps, a toaster, much more, 10 amps, and then automobile starter, you're getting greater, 150 amps, and then when you get down to like a wristwatch, now you're in the microamps, so 10 to the minus 6 again. And then important is enough to shock is a few milliamps, which is 10 to the minus 3 ampere. So it takes very little current to shock you. And so it's really important to be aware of that and to be aware of what you're doing whenever you're hooking up electrical circuits. Then we talk about resistance. Resistance and resistors do what kind of they say. They're basically resisting current flow. And so when we define it 1 ohm, it's typically measured in ohms. It allows a potential of 1 volt to cause a current of 1 ampere to flow in a circuit. And Ohm's law, again, like I said, this is a really important relationship where voltage equals I times R, or V equals I times R. And V is potential in volts, I is the current in amps, and R is the resistance in ohms. I just want to point out there that you can see that I is not A. So that's always something that used to be confusing to me. So just make sure if you see I in an equation like that, it's actually talking about amps. So just taking a look at this, you can see that as the current increases or the resistance, that the voltage is going to increase. But then you can also take the same equation and rearrange it, right? And so then you can get current equals voltage over resistance. And so in that instance, the current is going to increase as resistance decreases. So that's a really important relationship. Spend some time learning this. And then also our activity that we're going to be working with will also be dealing with this law. Also, we want to talk about power. So power is measured in watts, and 1 watt of power is produced when a potential of 1 volt causes a current of 1 ampere to flow in a circuit. And this is an important relationship. P equals I times V, or P equals current times voltage. And you can also take that previous equation of Ohm's law and start substituting in variables, and then you're able to measure power equals current times voltage, but then power is also equals to the current squared times resistance, or also equal to voltage squared divided by the resistance. So hopefully you can kind of, get a good understanding of that. I would say in both of those instances, the important thing is that as current or voltage increases, you're going to be increasing in power. And this matters whenever you are looking at selecting different electronic components to go into circuits. It's really important to keep an eye out for what the power rating is of the device you're going to use. So again, some examples that you could take a look at, back to the wristwatch. It's got, remember we talked about micro amps of current, and so you just get really small power with that system. But then you look at a flashlight, it's 1 watt. When we talk about our balloon radio beacon that we're going to be using, it's going to be, approximately 5 watts of power, and so forth. You can see, a hair dryer is 1100 watts. So as you continue on, you get to like the state of Louisiana, it's apparently 8,000 megawatts. I did not know that, so I'm just learning that for the first time myself. Yeah.
And it's even higher now.
Yeah, it's probably higher because this was probably done a few years ago. All right, so hopefully you get an idea about that. So now we're going to be using to talk about the digital multimeter. So this is a really important device that we use to measure various things. And in this, the rest of the presentation and in the activities, you're going to see it referred to as DMM. So just for digital multimeter, when you talk to people, most of the time just say multimeter, just so you're aware, it's all the same thing. So this particular device measures voltage, current, resistance, and sometimes other parameters. And the one that we're showing here should be the one that you're using. but there are various like other companies that create things. These things like Fluke is a standard one. Like normally those are like the orange or yellow ones that you find, and they operate slightly different than this. So you definitely, before you just pick one up and plug it in, take a look at what the differences might be from the previous one that you learned on. And just so you know, this is like a really inexpensive one, less than 5 volts. So I don't know, I'm hoping that you can see my cursor here, but I just want to briefly point out a couple of things. Yeah, okay, good. So when we are looking at DC voltage, it's going to sort of be this section right here, and we can see that it goes from 200 millivolts all the way to 1,000 volts. And this particular meter is interesting because there's sort of these different ranges that you have to select for that to operate in. So just always be aware of those different ranges. This will also measure AC voltage from 200 to 750 volts. And then over here we've got DC current. And in here they call it A instead of I, so just it goes both ways. But anyway, you can go from 200 microamps all the way to 200 milliamps on this particular setting. And this is really important. The most important thing that I'm going to tell you is just pay attention that this is how you would measure things up to 200 milliamps. And this one, you can see it says 10 amps. And so it is kind of pointing to this plug, and we're going to go over this in detail, but I'm just going to say it a few times because it's very important to pay attention to this. And then this HFE, it has to deal with this transistor area that we're probably not going to be dealing with much here. This is to measure whether or not a diode is working or not. And then this is to measure resistance. So it goes from 200 ohms up to 2,000 kilo ohms. So again, whenever you're looking at these different things that you're going to be measuring, you know, try to set this range here so that you can get the proper reading. And that's how this particular one works, but it may not be the way that a different meter works. And then also important over here is this, where the leads, hopefully with the meter that you're looking at, there's 2 leads. There's going to be a black lead and a red lead. And so the different configurations of that we're about to go over, but I just want to make sure that you understand that those will be plugged into one of these configurations here. And COM is another term that we often use for ground. And common means that it's a common potential that our circuit is being measured from. And then we have here this other, this is a bunch of symbols kind of together. It's actually voltage, resistance, and milliamps is how we're going to use to measure those different things. And then this one again is the special one that we're going to use to measure higher currents up to 10 amps. So this is how, again, just how do you take measurements with it? So you put that black lead in the bottom, and just a real quick note about the black and red. For circuits that sit on the bench top, you often find that black is ground. If you were to look at an AC wall socket, that is not the case. So make sure you distinguish, it's the black is hot, the hot wire. So when we're talking about circuits in this class and you see a black wire, oftentimes that is ground. If you are choosing wires to connect your circuit, it's always great to use black for ground. That way if somebody's looking at it, they say, oh, that is the ground wire. Just a note there. And then in this case, we have a red lead, and so it's again always nice to indicate that that is a positive. If you happen to have a choice of colors, red is a great color to indicate plus voltage. So in this instance, to measure voltage, resistance, or current up to the milliamp range, up to that 200 milliamp range, you plug the red into that terminal that's shown in this picture right here. And then again, you're going to select the proper range. And depending on the scope or the meter, you may not need to select the wheel. Now, to measure larger currents above 200 milliamps, you can use this upper plug, and you connect it to that for that. And so we're gonna go over that. I suspect that for what we're doing with the balloon program here, you're mainly going to be using the other the 200 milliamp current is probably going to be around the values that you're going to use. So you probably won't need to do that, but it's just important to know. So let's see. This is going to be what does that say up there? Hold on one second. So we're going to look at how to measure the voltage. And in order to measure voltage, you have to put the leads in parallel with the electrical circuit or whatever you're trying to measure. So that means you put it across it. So the simple battery and lamp circuit, and you're going to be looking more at this in the activity. So we're going to start with the battery. Everybody knows batteries. This is a battery holder, and this has a particular DC voltage with it. And then you have the red lead, that is our positive, and then we have the ground, which is the black coming out. And you can see that we also have a lamp here that we're going to light up. So if you just follow the current, we go around through the red, through the lamp, and then back around the black lead. So that's sort of how we complete the circuit. So if we wanted to measure the voltage across that lamp, we are going to put the leads across that the lamp in this position, and then you'll be able to see a voltage. And so I just want to make a point back again to Ohm's law here that we have the voltage equals I times R. So we have a current that runs through this system, and that is, we also have a resistance of the lamp as well. And so whenever you have a device that has a resistance and you have a current running through it, then you will get a voltage drop across that component. Again, you'll understand more of this whenever you do the activity. So to measure current, instead of being in parallel, you have to have the lead set up in series or in line with the circuit element whose current is being measured. So it's really important to have a good grasp of this concept depending on what you want to measure. And so if we just take a look again at how the current is flowing in the circuit, we have it coming out of the battery and around, and then it goes into the red lead, the positive lead, and then it goes out through the common lead, and it comes back around across the lamp and back to the ground of the battery. And so you can see that there's a big current loop here, and that this way our meter is in line with the entire circuit, and so it's going to measure the current across the entire circuit. And to measure the resistance, again, we're still on our voltage resistance milliamp lead here as well. And you're also important that I didn't point out between the last two, you have to turn the dial to actually read these different things that we're talking about. So when you're measuring voltage, you're going to be, putting it on the DCV range. When we did the current, it's DCA. And then for this particular thing, we've got the dial set to whatever resistance. So for this, we have the, again, this is a parallel situation where you just put the leads across the resistor leads, and then you're able to measure the resistance. And so for this particular one, we see that the reading says 976, and we have the range set to 0 to 2000 ohms. And so you can interpret this reading as 976 ohms or 0.976 kilo ohms. Those are different ways to look at it. And this is this section. This section is to try to help you whenever you accidentally connect something. You try to measure current with the voltage probes plugged in incorrectly. So if you connect the multimeter set to read current in parallel with the voltage source, such as a battery, then what happens is you kind of damage something. And there's kind of this old terminology where it's like the circuits work with magic, and so some of the magic smoke might escape from your multimeter. So you might damage it. Hopefully your multimeter will maybe have a protective fuse. And if it does not, you might actually damage your multimeter. So that's why it's really important to pay attention to how those leads are set up for when you're measuring current. and then also putting them back to the voltage whenever the voltage reading whenever you're done measuring that current. You should always check that. And this is just a closer look. If you do, or if you like, if this happens to you, or you happen to pick up one, you can just normally open it up. You can see that the fuse, it's normally like a piece of metal is in there. It's like broken. That means the fuse is blown, and then you can just look at the part number and order a new one. It's typically what happens. So the activity for today is to practice making the measurements with a digital multimeter, and hopefully you're going to be able to do this without blowing any fuses. And then you'll also be able to practice calculating the resistance and power using Ohm's law and the power relation.